Hello, this is John with Siptopia.org. Today we are going to dig into Session Description Protocol. We will use some analogies and examples in order to simplify the concepts. We will start with the question, what is SDP? And naturally we will look at this protocol purely from Session Initiation Protocol's perspective. After we answer that question, we will move on to the session description lines that make up the message body of SIP requests and responses. Finally, we talk about the SDP attributes and how they are used to extend this protocol. So what is SDP? Let's jump right into it. Session Description Protocol is a well-established format used by entities in order to agree on compatible media types and parameters for successful interactions like voice and video calls. And that's exactly why SIP uses SDP. People often think Session Description Protocol is a part of the Session Initiation Protocol. That is quite normal since SDP is the most commonly used protocol in SIP for defining session parameters for successful interactions between user agents. However, as we discussed in our RFC 3261 Simplified series, Session Description Protocol is just one of the protocols Session Initiation Protocol utilizes. SDP is completely separate than SIP. You can have a SIP session without using SDP. Similarly, you can use SDP for protocols other than SIP. Naturally, this is outside of our scope here as we are looking at the SDP from SIP's perspective. SDP provides the following information about the user agent's attempt to start a SIP session: session name and purpose, time period the session is active for, media types and formats the user agent would like to use, like audio and video formats G711, G729, and H.264, MPEG, etc. And finally, where the other end should send the media to, like user agent's IP address, transport protocol, and the ports it's listening for this session. Before we move into the technical mumbo jumbo, let's visit our old friend Tarzan from RFC 3261 Simplified Session Initiation Protocol series. Think about the time he first met Jane. Tarzan doesn't know which language Jane speaks and vice versa. So how did they start communicating? Let's say Tarzan speaks English and German, whereas Jane can only speak Spanish. So here Tarzan says, I speak English and ich spreche Deutsch, and Jane responds, yo hablo español. Well, they do not have a common/compatible language. They cannot talk to each other. Similarly, in the SIP world, if two user agents do not support a common/compatible codec, they cannot talk to each other. Now let's say Tarzan speaks English and German, and Jane speaks English only. In this case, Tarzan would say, I speak English and ich spreche Deutsch. And Jane would respond with, I speak English. They now have a common language and they can start talking to each other. In the SIP world, if a user agent supports two codecs and one of them is supported by the other user agent, they can use that common codec to start talking to each other. Please note that even if Jane can speak English as well as Spanish in the scenario, she will only respond with I speak English to Tarzan. Since Tarzan indicated that he is only capable of speaking in English and German and not Spanish, it would be unnecessary for Jane to indicate that she also speaks Spanish. Same logic applies to SIP. People who write these RFCs are not dumb. If a user agent says it supports codecs A and B, the other user agent should not respond by saying it supports other codecs than A and B. Finally, Let's say Tarzan speaks English and German, and Jane speaks both languages as well as Spanish. Going with the logical conclusion again, Tarzan would say, I speak English and ich spreche Deutsch. And Jane would respond with, I speak English and ich spreche Deutsch. Naturally, Jane doesn't add that she speaks Spanish after noting that Spanish is not one of the languages Tarzan speaks. They do speak two common languages though. Therefore, they can start talking to each other and at any time switch from English to German and vice versa. At this point, Tarzan and Jane could also decide to just speak English or German. User agents in a SIP call can also switch between codecs in this exact scenario. Okay, now let's have some fun by capturing traffic of a SIP call between Tarzan and Jane. Alright folks, in our environment we have a SIP proxy for California region and another SIP proxy for Texas. As you can see, Tarzan using this Linux instance with a SIP client is registered to California registrar, and he is using the SIP proxy here. Similarly, Jane is registered to Texas registrar, and she is using the SIP proxy in the Texas region. Now we are going to capture every SIP communication in this environment and then look at the details together. So let's go ahead and check out the codecs that are available right now to our SIP clients. As you can see, just like our first scenario, we have two codecs that Tarzan can speak, ULO and ALO, and Jane can only speak G722, which is not a common codec between the two. In other words, these two do not have any common codecs to talk to each other. Let's see what happens when Tarzan calls Jane. It's ringing. Does that mean it's going to be successful? Well, let's take a look. Oh, the call ended. Let's take a look at our capture. As you can see, we received a response from Jane that said 488 not acceptable here, and there's a warning SIP header field that explains the result. SDP incompatible media format, no common codec. So that is exactly what we expected. Let's go ahead and move on to the next scenario. In the second scenario, we had Tarzan speaking English and German, whereas Jane only speaking English. So let's see what happens when we use these codecs and these two call each other. So Tarzan calls Jane. Once again it's ringing. Let's answer the call, and the call is established and it's using ULO as expected. So let's end this call and bring up our Wireshark capture. Now we are going to look at a few things here. This tells us that Tarzan supports G711 MULO and ALO, and if you look at the 200 OK response, you see that Jane supports ULO. They do not show up here, and we are gonna discuss why. It has something to do with this AVP, Alien versus Predator. So let's move on to the next scenario. In our last scenario, we said Tarzan speaks both English and German, whereas Jane speaks both languages plus Spanish. So let's see what happens, what the exchanges are between the two. Tarzan calls Jane. Jane answers the call. And let's end the call to take a look at the traffic capture. Alright, so if you look at the invite request from Tarzan, you again see ULO and ALO G711 codecs, and the response from Jane included ULO and ALO G711 codecs, not the G722 that Jane supports, because there is no point in calling that one out. Before we go through individual lines that make up SDP, let's remember from RFC 3261 Simplified Session Initiation Protocol series that in a SIP header, content type column application/SDP means SIP is using SDP for describing session parameters. SDP is composed of a number of lines with the format type column value. If you have been using Wireshark to analyze packet captures, you might have noticed these single letters within parentheses in each line. Well, the type in RFC 4566 are these single letters and not the nice line descriptions you see in Wireshark captures. In other words, the lines in our example are actually just rectangles shown here without the nice explanations Wireshark kindly adds. You may also look at the decoded raw data to confirm that the SDP actually doesn't carry these nice explanations we normally see in Wireshark. This one, for example, shows that the real captured data has just V equals 0 and not the nicely put line that says session description protocol version equals 0. Before we dive into these type letters, it is also worth noting that structure-wise, SDP is composed of a session level section followed by 0 or more media level sections. Session level section can be considered the global configuration parameters that apply to all media streams. In this case, media level sections can now be considered local configuration parameters. As you can guess, in case of an overlap, the local configuration parameters override the global configuration parameters for that specific media stream. If there is another media stream without a local configuration parameter, this global parameter applies to that stream. Now, these are the most commonly used description types, and other than C and A, they are all mandatory. It is important to know these type letters so that you are not surprised when you see these in some applications and not the nice explanations Wireshark adds to the lines. Unless you are a developer, this will probably be not too important, but this order of these lines is also mandatory. For example, every SDP starts with type V. Type O is always below V. Type S is always below O, and so on. Well, with this info, you can also guess that every session level section starts with V-type description and ends before the first M-type description. If there are multiple media streams, each media level section starts with an M-type and ends before the next M line. The last media stream naturally starts with an M-type description and ends at the bottom of the SDP body. Now let's go over these descriptions and focus on certain aspects that are crucial for troubleshooting SIP calls. First of all, there is no other version of SDP, so you won't see anything other than 0 in the V-type description. The type O is slightly more important. The FQDN or IP address seen at the end of the O-type description represents whoever put this SDP into this SIP message. In our test calls, Tarzan's SIP client sent the invite request with the SDP message body. Therefore, Tarzan's SIP client's IP address is represented in this screenshot. The type S is simply a name given to the session. It doesn't have to be meaningful, but it has to exist, even if it's just empty space. Now, one of the most important values to pay attention to when troubleshooting SIP calls is the IP address in the C type description. This is where the SIP client tells the other end where to send the media to in order to reach this end. In other words, C is the IP address other end must send RTP packets to in a SIP call. If a call is established and you do not see any traffic coming into this IP address, you have a one-way communication problem. Unless each media stream has their own C description, there must be a C description in the session level section. As mentioned before, this is more like a global configuration. Each media stream could overwrite this IP address by defining their own C value or keep this global IP address. Another mandatory but rarely used type description is T. It shows the start and end time for a session. Most of the time, these values are both 0, meaning there is no time restriction or bounding for this session. As explained earlier, the session level section of an SDP structure ends with the first M type description. This is where we define the media streams, what it is that we will be exchanging in the SIP call, video and/or voice. The first parameter in the M type description indicates whether this call is a video or a voice call. In our test calls, Tarzan has been calling Jane with a SIP client that is only capable of voice calls. That is why the first parameter in this screenshot is audio. The next parameter is the port that this SIP client will be listening for media. Combined with the IP address in the C type description, this port provides the transport address the other end must use to send RTP to in order to reach this client. This combination of IP address and port, aka transport address, is the single most important value used in troubleshooting SIP calls. If there is one thing to focus on in a SIP call troubleshooting, it's this transport address. 99.99% of the time, the following parameter is RTP/AVP. Until I read RFC 3551, I thought the AVP here was Alien versus Predator. The numbers following RTP/AVP are payload type numbers, and they represent the payload formats this SIP client supports. Now, apparently AVP stands for Audio Video Profile, and RFC 3551 lists a bunch of static mappings between payload type numbers and payload type formats. For example, payload type number 0 represents payload type format G711 ULO, whereas 8 represents G711 ALO. Since these are static mappings called out in RFC 3551, the real SDP body actually doesn't have a nice explanation like media format G711 PCMU. The decoded raw data only has payload type number 0, and that's it. The rest is added by Wireshark to make it easier for human readers to understand the payload type number to payload type format mapping. Well, if there is a static mapping of payload type numbers to payload type formats, there must be a dynamic mapping as well. Let's go back to the jungle and run another test call between Tarzan and Jane with a few more codecs to have a nice example for dynamic mappings. Alright folks, we are back to our test environment. As you can see, we are also running a Wireshark to capture the SIP traffic exchanged in this environment. Now in this scenario, Tarzan has a SIP client that supports 5 different codecs, and Jane similarly has another SIP client that supports 5 different codecs. If you take a closer look, you will notice that 3 of the codecs in these lists are common. Let's apply the concepts that we have learned in our previous discussions to figure out what the SDP message bodies will look like. If we simply consider these as languages Tarzan speaks and these as languages Jane speaks, we can use the same analogies that we used earlier. So in this case, Tarzan will tell Jane that he speaks these 5 languages in this order. Jane, in response, should only tell Tarzan that she also speaks the languages that they have in common. So while we expect to see all these codecs as options in Tarzan's invite request, we should expect a different list than this in Jane's response. Let's try to figure out what that should be. Naturally, this first codec is not supported by Jane, so it won't be in her response. G711 ALO is supported by Jane. Specs isn't, whereas G711 ULO and GSM are both supported. So the order here is very important, and as a result, Jane will respond in that order. So we are expecting to see Jane's response with codecs G711 ALO, G711 ULO, and GSM in that order. Therefore, the initial codec that Tarzan will prefer is going to be G711 ALO. Let's run a test call and see if that's the case. Let's close these windows and give Jane a call. Alright, the call is coming, we answer the call, and we immediately confirm that Tarzan is using, well, the call is using G711 ALO. Let's end the call, take a look at our capture. As you can see in message body, Tarzan offers all the codecs that we had in his list, whereas Jane responds only with the common codecs that they have, starting with the first one that they had in common, which is G711 ALO. This is the SDP message body in Tarzan's invite request. Let's compare it with the list of codecs we configured prior to the test call. As you can see, SDP lists the codecs in the order of preference configured in the SIP client. It is worth noting that since ILBC and specs codecs are not listed in the RFC 3551, they do not have a static payload type number versus payload type format mapping. In other words, while payload type number 8 means G711 ALO to all SIP endpoints, 98 doesn't have a common meaning. That is why Tarzan's SIP client adds SDP Attributes to define, aka dynamically map, payload type number 98 to payload type format ILBC. Now the other end knows that Tarzan is referring to ILBC with the payload type number 98. Similarly, Tarzan is also using SDP Attributes to dynamically map payload type number 110 to payload type format specs. Since these are dynamic mappings, in other SIP calls, payload type number 98 might not map to ILBC or 110 to specs. However, payload type number 8 will always be associated with payload type format G711 ALO, as it is listed as a static mapping in RFC 3551. Unless you are a developer, you do not really need to know which payloads are listed in RFC 3551. For example, since GSM is not dynamically mapped in an SDP attribute in this screenshot, it must have a static mapping to payload type number 3 in RFC 3551. Well, apparently GSM is indeed mapped in RFC 3551 to payload type number 3. Now this is the SDP message body in Jane's 200 OK response to Tarzan. Naturally, Jane responds with the codecs/languages that they have in common. An important point here is that the order of preference in Tarzan's SDP is applied in Jane's response as well. That is why, even though Jane prefers GSM and G711 ULO over G711 ALO per SIP client settings, the 200 OK response has G711 ALO listed at the top. As we have seen in the previous slides, G711 ALO, G711 ULO, and GSM all have static mappings to payload type numbers in RFC 3551. That is why there is no additional SDP attribute to dynamically map these codecs to payload type numbers. Since it's the first choice of codec, Tarzan will start using G711 ALO for audio. However, at any time during the call, they can change the codec that they use to G711 ULO or GSM without additional SIP messages exchanged. Tarzan could also send a re-invite request at any time after the call is established to fix the codec just to G711 ALO. That would be accomplished by sending an SDP message body that only lists G711 ALO as the codec supported. Tarzan already knows at this point that Jane supports G711 ALO. There is no risk of losing the communication if Tarzan insists on only using G711 ALO. Well, we have already covered the single most important SDP attribute, RTP map. It is used to dynamically map payload type numbers to payload type formats. What about the FMTP attribute that follows some RTP map attributes? Looking at the codec selection we made for Tarzan's SIP client, we noticed that the codec ILBC could have two modes, 20 and 30. Naturally, the RTP map entry for ILBC mode 20 will be the same as ILBC mode 30. This mode is the difference used to distinguish the two versions of ILBC. In other words, mode parameter is important to differentiate the two ILBC codecs from each other. That is where FMTP comes into play. FMTP is used to support the dynamic mapping with certain parameters that may be necessary to distinguish the codec. Obviously, not all dynamic mappings need FMTP to define codec parameters. Specs, for example, was dynamically mapped to payload type number 110 without a FMTP entry for codec parameters. To summarize, the most common SDP attribute, RTP map, is used to dynamically map payload type numbers to payload type formats so that both SIP user agents refer to the same format with the same number. Time to time, FMTP is used with RTP map to support the dynamic mappings by adding codec parameters. Let's finish up the SDP attributes section with the two that show up in most of the SIP calls. As you know, there are different ways to relay DTMF tones. The most preferred method is defined in RFC 2833 as DTMF in RTP payload. That is what telephony-event is. DTMF in RTP payload, aka RFC 2833. Supporting this dynamic mapping is the FMTP for 0-15, meaning the tones from 0 to 15 are supported. It's important to pay attention to this attribute as its absence means the user agent does not support RFC 2833. Finally, an attribute send-receive/send-only/receive-only will signify if the user agent is willing to talk and listen, just talk but not listen, or listen but not talk respectively. In its absence, user agent should be assumed to be send-receive, aka both talk and listen. This concludes our tutorial, RFC 4566 Simplified Session Description Protocol. If you have any questions or comments, please let us know.